Okay, so we're going to start with trig graphs. The notes will be maybe a little bit longer than the last couple of times because it's reviewing the investigations you did. If you did a good job on those, hopefully all the beginning stuff will be review. So the first thing that we want to do is we actually want to fill in both the sine and the cosine graphs for this lesson. That's going to be our focus on how to get graphs of those. And in order to do that, I'm going to refer to a couple of things in your investigations that you could have got some information here for this parent function page of your notes. And then we'll go into how to do the graphs. So if we look at the investigations that you guys did, the first investigation was about an introduction to the parent functions. So on slide 3 of that, you saw this trig function. And it then talked about amplitude and period. So I just want to point out that amplitude is how high up from the midline you go. So the midline is here, like a middle of the function that would cut it in half. So the highest point is 1 unit above the midline, and the lowest point is 1 unit below, and that gave us our amplitude. Period is how long it takes to complete one cycle of the graph. And you see that here if you slide along the graph from 0, you get to this point right here, you've completed the cycle, and then you start going through it again. So that point right there is a distance of 2 pi from 0 horizontally, so the period was 2 pi. You should have seen the same thing with the cosine function. If you haven't looked at these carefully yourself and done the investigation, when I look at the cosine function, you might think that this is no different than the sine function. And if I removed the axis from the background, I would agree with you. The only difference is you see that it starts up here at the maximum value of 1 and then goes through the cycle. But again, the cycle is 2 pi and the amplitude is 1. That's because sine and cosine go through the same values around the unit circle. The x and y coordinates, we see the same things happening. We just see them happening at different times for x versus y. So it's basically just like one shift over for the graph. And then for tangents, you guys should have seen that they were different. We're not really going to build the tangent parent function today, but you should have saw a picture like this, which has actually been split into all these branches that are disconnected by asymptotes, because there are places where the tangent is undefined. And then that creates an asymptote on our graph. So we're going to take this information and we're going to fill in the actual parent functions on our note guide. So we're going to fill in those points that we saw for sine. And to make notations so that we can graph these the same way you guys did transformations with all of your other functions, you may choose to do this, or you may choose to actually just use the patterns that you see here and not points and get the graphs. It's up to you, but we're going to do the chart the same way that you guys have. So if you went around your unit circle and you evaluated the sine function at 0, it'd be 0. At pi over 2, it'd be 1. And the rest of these values that you see here. So I'm actually going to label my graph so that I reach through this one period. And 0, 0, pi over 2, 1. I'm going to make those by 1s. Pi 0, 3 pi over 2, negative 1, and 2 pi 0. It's one period of the sine function. And we're going to really focus on graphing one period and then continuing that after we've seen the pattern and how to scale a graph. So the period here, 2 pi, and the amplitude is 1. I'm now going to do the same thing for the cosine graph, and you guys saw how similar that the cosine was. The only difference is that when we plug in these angles for the cosine, and notice we did pick the friendliest ones as far as ease of plotting, that when you plug in 0 for cosine, you get 1 instead of 0, like the sine function. And so you see it cycle through the same values, but it's slightly different places. So I'm going to scale all of this the same exact way I did because I'm seeing really similar patterns. It's just that here I'm at 1, and at pi over 2, pi, 3 pi over 2, and 2 pi. And that pattern looks like this. They really are creating the same pattern, but like a different starting point if you wanted to refer to it as that, given that there's a different value at the starting angle of 0 for a sine function than there is for a cosine function. And this would make them have these very similar characteristics, that the cosine also has a period of 2 pi and an amplitude of 1. And I'm actually not going to put our tangent parent function in right now. I'm going to wait until we talk about our tangent graphs for that. So we're going to focus on these two graphs for now. Tangent we'll also do this week, and then next week we'll just do the 3 reciprocal functions. And we will then be testing at the end of that week. This unit's super quick, and we're really relying on your previous information about graphs in order to do this. Oops. So we're going to look at a couple of things from the Desmos investigation then that you did about transformation specifically. So the first investigation just got you used to what these graphs would look like and where they came from. And then the second investigation, its purpose was to show you transformations. So I want to emphasize 2 of them and then summarize them in your notes. The first one I want to emphasize is when we changed the a values. So the black graph that you see here is the parent sine function. The blue graph that you see is the same sine function, the only difference being that the a value became 2. And notice that it has all the same zeros. It hit the axis at exactly the same place. The difference is that it reaches higher maximums and lower minimums. And remember, we referred to that distance from the middle as being the amplitude. So that a value that's causing a vertical stretch here is literally taking the amplitude and stretching it out further. If you wanted to contrast that with putting in a smaller a value, again, this black graph is the parent function, and the green one is changing to a y value of 1/2. Notice again, they share the same zeros. However, the max and min on the green functions have been vertically shrunk down. They are closer to the axis than they were in the parent function, because that 1/2 is a vertical compression and is making our amplitude smaller, okay, and essentially half of what it was originally. I also want to look at the period, and hopefully you guys saw what changed the period, and that was the b value. So again, the black graph that you see here is the parent sine function. And then notice when you make the b value 2, like in the blue graph here, what you're seeing is you're seeing twice as many sine graphs fit onto this picture. That's what the 2 is standing for. But remember, what that means on the graph is that this graph takes half as long to complete the period. Notice it completes 1 cycle of the graph in pi because it's taken the graph and it's horizontally compressed it. Even though the number is 2 here, the horizontal distance is not getting multiplied by 2, it's getting cut in half. Conversely, if we change it to 1/2, you can see that the green wave here is really stretched out, okay? That if we look at it, we see that to get from the beginning to the end of one period of the green graph takes double the amount of time that it normally takes the parent function. So that 1/2 that's in the equation is saying that you're only going to get half as many cycles in as you normally do. Therefore, the period of the graph is getting stretched out double the distance that it used to be. So we're going to summarize these things in your notes. So the a value is still causing vertical stretches and reflections. So those are things that are not new to you. That is causing vertical stretching and compressing, and also a vertical reflection. So this should be review. Vertical reflection means over the x-axis. This is when it's negative. But the stretching, the vertical stretching and compressing means it's going to change the amplitude. The b value, again, review, in the way that we're saying it here, would cause horizontal stretching and compressing. and it would cause horizontal reflecting. And that means reflection over the y-axis. But something new for us here is that now when we have a horizontal stretch or compression, this is affecting this characteristic of the graph called the period. The h value is still going to shift your graph left or right. And the k value is still going to shift your graph up or down. So as we go through and we graph them by hand, I told you guys we can make the chart or we can use characteristics. So they kind of wrote some things out here that, some things we saw. The amplitude can basically be determined by the a value if you don't look at the reflection. Okay, so they're saying the absolute value of a is the amplitude, but that these other graphs don't have an amplitude. So you'll see those graphs all have asymptotes like the tangent function, so they behave a little differently. And then notice how they say we're determining the period. So a couple of notes about this. If normally your sine or cosine function has a period of 2 pi, but let's say I put a 3 in the b value, normally when we make our chart, that means all of our x's would have a horizontal compression of 1/3. Since the period is a horizontal measurement, it too is going to get compressed by 1/3. Making our period 2 pi over 3. So I like to think about it just like we've always done. Like in my chart, I'm horizontally compressing. Since my period is a horizontal measurement, I'm horizontally compressing. But oftentimes you guys will see them write it in a formula like this. You see the same thing for tangent, but you notice that tangent has a pi in the numerator because tangent has a smaller period than sine or cosine, and we'll discuss that more extensively in the next notes. So now we're going to do a couple of examples. So we're going to start with this function. So first, rewrite it so you can see all of the characteristics. And we've practiced this all year. We don't want that 2 distributed to the terms inside of that sine function. Oops. We want to undistribute it. And this would be x minus pi over 2 because I took each of those terms and divided them by 2. So the transformations that I'm seeing, my a value being a -2 tells me 2 things. The negative tells me I have a reflection over the x-axis, and the 2 tells me I have a vertical stretch by 2. The b value of 2 tells me that I have a horizontal, and remember I'm not actually going to use 2, everything's going to get multiplied by 1/2, making them smaller. That means this is actually a horizontal compression by 1/2. My h value is pi over 2, so I'm going to shift right pi over 2. And my k value is 1, so I'm going to shift up 1. So I'm going to go through and do a couple of things. If you want to, these characteristics, you now know the period. So normally the period's 2 pi. You see that you had this horizontal compression by 1/2. So you would now know that your period is pi. Okay. And your amplitude is normally 1, but you had a vertical stretch by 2, so you would expect your amplitude to be 2. So one way of graphing these is to know your parent function really well. Your parent function goes through 5 points total, starting at 0 and ending at 2 pi, and for sine the points are on the midline, then up to 1, midline, back to 2, there. Okay, like this. So if I were to graph this just by knowing the shape, if you don't want to do the tables, here's what I would do. First of all, where is the midline of this function? So did it get shifted up or down? And it did. So the midline of the function, it was shifted up 1. So this is not really part of my graph, but I'm just going to put it here as a reference. I expect this to be like the new 0 for my function. Then, okay, My amplitude is 2, so those high and low points I expect to go 2 units above 1 and 2 units below. How I'm going to scale the graph, I'm going to use my period. So normally my period was 2 pi, so I liked that fourth mark after 0 to be 2 pi. Now my period is pi, so I like that fourth mark after 0 to be pi. And if I am unsure, if you're a little bit unsure about how I'm about to do this, I'm about to split that into 4 parts to learn that that means I'm technically scaling my graph by pi over 4. So that would be 1 pi over 4, 2 pi over 4, or pi over 2, 3 pi over 4, pi, and then we would keep numbering in this way. And the values you see me right here are pi over 4s, but then reduced if possible. So I'm writing them out. And on the other side, you would have those same values in their negative format. So now basically, I just want to put the set of points on the graph. Let me finish labeling this for you guys. Okay, that's probably good enough. I want to put like this consecutive set of points on the graph. Kind of like a step function, I might want to see if it's reflected first, which it is. It's reflected over the x-axis. So when I draw these points, I'm going to have to draw them like this. So I want to start here, but my graph's going to go down first and then up. So I now basically have everything I know, except for I need the starting point. So I normally am starting at an x value of 0. But notice this graph has been shifted right pi over 2. So I'm going to go over to pi over 2. And that's where I'm going to put my point on the midline. So that's like this point right here. Then I'm going down, back to the midline, up, back to the midline. So I'm going down, but 2, because the amplitude here was 2, back to the midline, up, back to the midline. This makes one cycle, or one period, of this sine graph. If you don't like this method, okay, this just works because it has these special characteristics. You could go back and do the same method that we've been doing in all of our previous graphs. So that would be to take your parent function. If you guys have to pause the video, then pause the video to copy down the points, and then do the transformations. So based on what we see here, x would go through these transformations, y would get multiplied by -2 and then add 1, and I'm just using my a's, b's, h, and k values to say what would happen. And then when you do that, you would get these points. And you notice they should match what we have over there. I'm making sure here. Okay, and then plot them. So you can do it with points if you prefer to do the same transformations we've always done, or you could use the characteristics of this function, and then you want to continue the pattern so that we understand that you know that you can graph at least 2 periods of this function. So there would be another period of this function. Okay. I could continue it again if I wanted to. There's another period. You could go in the other direction. Okay. And then characteristics wise, we're just going to focus on domain and range here as well. So your domain for these functions is all reals, and your range, notice that the function keeps bouncing between 3 and -1. So you could say it like this, or in interval notation, you could do the domain and range with that notation. All right, we're going to look at another example, this time a cosine graph. So again, make sure you understand the setup. So in this graph, it's like a b value of -1/3 the way this equation is written. So with the 3 in the front, my A value of 3, I'm seeing a vertical stretch by 3. With my B value of negative 1/3, there's 2 transformations there. There's a reflection over the y-axis, and there's a horizontal, and remember the B value won't be used like 1/3, things will get multiplied by 3, so that makes it a horizontal stretch, again things getting multiplied by 3, and then with this K value of -2, there's a shift down 2. So again, if you want to use the tables, use the tables. I'll go through and do them at the end, but I'm going to do it the other way first so that you guys can see that. So period is normally 2 pi. There was a horizontal stretch by 3. This is going to make the period 6 pi. Amplitude is normally 1 for a cosine function. There's a vertical stretch by 3. This is going to make the amplitude 3. So remember, when I'm going to graph, I know that my general cosine graph starts at the max and goes again, 2 pi is the 4th value, through this sequence of points. And this is because I have the parent function memorized. That's still an expectation. So this is what I'm normally looking at. So again, I want to identify my midline. This function was shifted down 2. So my expectation is, instead of the midline being here on the axis, like it was for the parent function, the midline of this function is going to be at -2. Then I want to understand what my amplitude is, so I understand how high my highs go and how low my lows go. My amplitude is 3. So I expect the highest points to go up to reach 1, and the lowest points to go down to reach -5. And now my period, normally I would expect this 4th mark to be 2 pi if there was no horizontal stretching or compressing, but there was, so I'm just kind of changing how I measure it, and I would like one period to extend all the way out to 6 pi. And again, then I have to know what to count my graph by. So I'm going to take 6 pi, since it's the 4th mark, and split it up into fourths. And that's going to give me 3 pi over 2. So that means each mark on this graph is 3 pi over 2. So 3 pi over 2 plus another 3 pi over 2 is 6 pi over 2, which is 3 pi. And then 9 pi over 2, 12 pi over 2, which is where the 6 pi is coming from, 15 pi over 2, 18 pi over 2 is the same as 9 pi, 21 pi over 2, 24 pi over 2, which would be 12 pi, etc. And then those same values would exist going out in the negative direction. So I'm just going to set up at least a few of those here. Okay. So now I'm just going to check reflection and starting point. So this graph had a reflection over the y-axis. So think through what that would look like. That means instead of me starting here and following this path towards the right, I want to reflect all the points the other way. So this point's getting reflected over here, and I'd continue that pattern. So I'm going to start here, but I'm going to go this direction with my points, not this anymore due to my reflection. These end up being the same, but not in all functions. Like for sine function, it would look different. So I know to start at a point, to go this direction with that pattern because of the reflection. I know the midline and the amplitude, so now I just want to know where I start. So was there any shifting horizontally? And there wasn't. So I actually do start at 0. So at 0, I'm going to mark a max value, which I said is going to be at 1. And then 1 unit over, I'm going to be at the midline. And then the next unit over, I'm going to be down at the minimum, then back at the midline, then back up to the maximum. This is 1 cycle or period of that function. And then if you did it by points, you should have seen the same things. And if you have to pause it because my scaling is too fast for you, you can do that. So cosine parent function, it's like this. And the transformations you would do here, horizontally, the reflection and the stretch, vertically, the stretch and the shift. And so you would see these values. And those would match the points that we got. And then for this function, if you were to continue this cycle, this was a maximum, you'd go back to the midline, down to the minimum, back to the midline, up to the maximum, down to the midline, back to the minimum, back to the midline, back to the maximum, and you could continue several periods of this function. And then the domain for this, again, is all real numbers, or if you like that interval notation, negative infinity to infinity. And the range, this function hits maximum at 1 and minimum at -5. So -5 less than or equal to y less than or equal to 1, or from -5 to 1. All right, for the sake of the time of your video notes, am not going to go through the entire example 3. I will post an extra video if you want to go through and do it. I'm just trying to be cognizant of what you may have going on. I just want to point out here that the horizontal stretch or compression is pi over 6, which means it's going to end up being a horizontal, let's see, things would get multiplied by 6 over pi. 6 over pi is like 6 over 3.14, which is a little bit less than 2, but it is more than 1. So this will be a stretch. And I just want to point out that your points are going to be very strange when you do this. You're going to be used to labeling your x-axis by radians, so you're going to want to label by like pi's and pi's over 2's like we've been doing. But in this one, notice because the horizontal stretch has that pi in it, watch what happens to your x values when you go through them. So when you do pi over 2 times 6 over pi, you would just get 6 over 2, which is just 3. And when you do pi times 6 over pi, you're going to get 6. And when you do 3 pi over 2 times 6 over pi, you're going to get 9. Then you're going to get 12 here. So notice it's going to be maybe strange that your x-axis is actually just labeled by like 3's probably, which is a little different than how we've been using them, because we tend to think of radians as having a pi in them, though they wouldn't need to. And your period would then also be affected by that, and your period here would just be 12 instead of a number that has that pi in it. We just want you to be aware that that can happen, okay? And again, I can put a supplemental video with the answer to that example. So we are going to then talk here about writing equations. So to write a sine equation with these characteristics, remember that amplitude basically tells you the a value. A reflection over the x-axis tells me that a should be negative. A horizontal shift right 4 tells me that, or right pi over 4 tells me that b should be positive pi over 4 when I plug it in. So these ones are a little more straightforward. I would expect a -2, then the sign for my equation. I would expect an x minus pi over 4, because remember it's x minus h. I'm sorry, I wrote b here, but for the horizontal shift, we're talking about h. So x minus pi over 4. Doesn't say anything about shifting up or down. So then I want to talk about the pi over 12, the period. Remember, you've been taking 2 pi, multiplying it by the reciprocal of b value to get the new period, which they're telling you is pi over 12. So you have to figure out how this happened. So you could just kind of cross multiply here. This would be 24 pi equals b pi. And if I divide both sides by pi, I get that I would want b to be 24 in this problem in order to get a period of pi over 12. And if you want, you can check. If you were given an equation with 24 to find the period, you would take 2 pi and you would multiply it by the reciprocal of 24. And that would give you pi over 12. To find the equation from a graph, you want to do all the same things that just happened. So if you understand how to do it with the written information, you want to find the written information from the graph. So first, can you see the amplitude? So this goes down to -4 and up to 2. That's 6 units total. So like -1 would be the midline of this function. So that tells me something right there, that it's shifted down 1. K is -1. And then the amplitude is 3. If I want to know the period, I have to see how long it takes to make a cycle. So notice one cycle of this graph goes from pi over 2 to 3 pi over 2. So 3 pi over 2 minus pi over 2 is a difference of pi. So the period is pi. And then the h value is going to be a little bit different. So here's what I want to point out so far. This list actually gets you both equations. If I'm writing a sine equation versus if I'm writing a cosine equation, for my sine equation, I see the amplitude is 3. I then write the word sine. For the b value, if the period is pi, remember what you have to think. 2 pi was horizontally stretched or compressed to produce a period of pi. And then you can solve to see what b is. And b should be 2. So the b value there is 2. Okay. And this so far would be true for the cosine also, an amplitude of 3. Sine and cosine have the same type of period, so that works out. They both have this midline, and that was shifted down 1. The only difference for the sine and cosine function is going to be the h value. You have to visualize the function. So what I mean by that is if you see where I've outlined the function in red, this looks like a cosine because it starts like the parent cosine function would start. That means this is a good starting value for the cosine, and I could use pi over 2 as a shift right. Now, don't get me wrong, that's not the only thing I could have done. I could have chosen negative pi over 2. That looks like a nice cosine graph. I could have chosen to start at 3 pi over 2 and done that. There's lots of different starting places. So there's lots of different answers to this for the h value. I would have to check and make sure that you wrote one that made sense. Now for the sine function, visually for the sine function, we like to see the parent functions start on the midline and go up and then down. So for example, like maybe right here would be a good place. And that would be one sine function. So that's happening halfway between 0 and pi over 2. So that would be pi over 4. And so I could use pi over 4 as an h value for the sine function.